Hello everyone, my name is Devarshi Joshi and welcome to this video presentation on 5nm Next-gen Semiconductors. This is currently under commercial production and let us see how it works. In this presentation, I am going to talk about the introduction to semiconductor industry, the basic laws driving the semiconductor industry, the previous 7 nanometer node process to understand the 5 nanometer process, the changes that were brought in the 7 nanometer process to achieve the 5nm node, and what is to be expected from the semiconductor industry in the future. The semiconductor industry is running and struggling to provide us with the technology we use to ensure comfort in our lives. With a lot of their investments into R&D, they are trying to make technology come handy with its features like faster processing, portability, voice control, artificial intelligence, and much more. Consider this for an example. There is 99% chance you might be watching this YouTube video on your laptop or on your smartphone, which means most of you are viewing this at your desired place and moving from one place to another if need be. So what if I told you that the first computer was so heavy that you along with 15 people wouldn't be able to lift it up, for it was of the size of a big room? ENIAC, Electronic Numerical Integrator and Computer, was the first ever computer built. It contained almost 10,000 capacitors, 70,000 resistors, 1,500 relays, 17,000 around vacuum tubes, which made it really heavy. Apart from this, another interesting fact about ENIAC is that its total power consumption was 160 kilowatts. That is a huge number. Compared to that, the current i7 and i5 core processors, which are an integral part of your laptop and other devices, only consume power closely around 200 watts, which makes them more efficient and faster processing. So it is clear that the necessity for a lower nanometer number is for the better performance and higher efficiency. Along with this, another important factor is the consumption of chip size. The smaller the node, the smaller the chip size, implying more transistors in less space, which will ultimately help in reducing the device size and increasing features by adding any new components in the saved space. The semiconductor industry started fabrication in 1971 and has been running ever since. The process started with a 10 micrometer process and it's currently at 7 nanometer process. The next production is currently happening for a 5 nanometer process, which has started commercially. The future is supposed to be a 3 nm process, which will be soon achieved in 2022. The advantages of using a smaller nanometer technology are smaller chip size, lesser power consumption, and more cores in the same space. Hence, there are so many industries that are into the process of making it. At the start of the chip fabrication, there were many companies who were running the race, out of which Samsung, Intel, TSMC, Micron are the few who have still continued to be in the race. The other additional advantage of this growth is that technology keeps getting cheaper and cheaper. The dollar per transistor keeps decreasing with every advancement in the technology, which is a good thing. So now let us talk about the basic laws that were actually the driving forces of the semiconductor industry. The first of which has to be Moore's Law, named after Gordon Moore, the co-founder of Fairchild Semiconductor and CEO of Intel. This is the main law. The law states that the number of transistors in a chip will double every 2 years. This was the breaking point in the semiconductor industry. This is what kept driving, because after every process that came out, in 2 years there was another process which could reduce the number of transistors, the transistor size, and increase the number of transistors in a chip. The other laws, like this one, Dennard scaling, was named after Robert H. Dennard. It is also known as MOSFET scaling. According to this, as transistors get smaller, the power density remains same. So the power used stays in proportion with area. Both voltage and currents can be scaled down with length, which is an important factor when manufacturing a lower and lower nanometer process. Coulomb's law is a combination of both Moore's and Dennard's. It says that the performance per watt grows faster. That is, the doubling rate is almost close to 1.5 years, which is a good law to define progress in an industry. Now let us talk about the semiconductor device fabrication. The semiconductor device fabrication is a lengthy process. It consists of so many steps. The wafers are first sewed and then they are polished. Then these material, this polished chip, the polished wafer, has material deposition on it. A resist is then added onto the layer, and then by lithography we actually implant patterns on the resist. The next process has to be etching and heating, which is to make sure that the print is developed. The next step is ion implantation, which is followed by removal of resist. This whole process is repeated a lot of times before we can declare that a wafer processing cycle is complete. After this, they are tested and they are packed into a plastic packaging so that it can be supplied to wherever is required. So, what does the 7 nanometer process bring? The 7 nanometer process brought the device performance to increase by 40% more than the 14 nanometer process, and the power consumption decreased by 60%, which is a really good advancement. In 2015, IBM demonstrated that 7 nanometer node chips with silicon germanium transistors could be used. The technology for lithography was EUV, which is extreme ultraviolet lithography. That is a pattern implanting process which is more efficient than normal lithography, almost 7 times. The transistor density was believed to be 4 times that of the 14 nanometer chips. The 7 nanometer scale MOSFETs were first demonstrated in research by around 2000s. The SiGe, or silicon germanium transistors, are much of a new technology that was used to integrate mixed signal circuits. As you can see in the figure, it is clear that both silicon and germanium is used to form the base of the transistor, which is not a usual thing. So heterojunction bipolar transistors have high forward gain and low reverse gain than traditional heterojunction bipolar transistors. This is the reason why silicon germanium transistors were used. This actually implies that the transistors had low current and high frequency performance, which was very good for the transistor. Now, considering silicon germanium on insulator SGOI, it increases the transistor speed and makes sure that the electron mobility and drive currents are higher, which means the processing speed would increase. The 7nm process was achieved by using FinFETs, which is FIN FET, effect transistors. The commercial 7nm node was thus achieved in 2018, and it used the EUVL lithography, as we already talked about. These FinFETs are called multi-gate MOSFETs. So let us understand how a FinFET works. The FinFET stands for field effect transistors, FIN field effect transistors. As you can see in the figure, there are 3 fins. In the FinFET, the gate is covering on all the 3 sides, which means there is very little leakage, and the main aim for development of FinFET was to reduce the submerged leakage path. The 5nm process, however, couldn't survive on the 7nm process. There had to be a difference. It was a struggle, and Samsung and TSMC began its production in 2019. They were confused between using GAFETs or FinFETs, but the FinFET technology wasn't up to the mark. Still, they could achieve the 5nm node by thinning the gates of the FinFET. The commercial 5nm node began this year in 2020, and the next process of 3nm nodes is planned to be achieved by 2022. Another important change from the 7nm process to the 5nm process is the use of synthesizable junction locked PLLs. PLLs are critical clocking circuits in virtually all digital applications. So what they actually do is they are timing generators. They are clock signals. So that is how a computer knows when the next operation is supposed to be done. So the scientists at Tokyo Tech built the smallest all digital phase lock loop. The synthesizable injection locked PLL was supposed to operate faster using a smaller area. So this techniques addressed 3 major concerns, which is decreasing required area, power consumption, and jitter, which is unwanted time fluctuations when transmitting digital signals. The previous PLLs up to the 7nm process required analog components which were bulky and which were very difficult to scale down. This RO based PLL, which is ring oscillator based PLLs, are affected by supply and devices. So that cannot be used for a 5nm process because it would cause more and more errors. The next generation large scale mixed signal silicon on chips would require flexible clocking circuits. So a fully synthesizable injection locked phase locked loops PLLs were used for digital clocking. As you can see in the figure, it is clearly stated that the FOM was reducing, or the negative FOM was reducing and the FOM was increasing, which is short for figure of merit. It was increasing for a smaller area. So the PLLs help to achieve that. It has 2 advantages: higher FOM and smallest chips area. The core area of this PLL was 0.0036 micrometer square. So to reduce the area of this PLL, a ring oscillator was used to dampen the phase noise, which was the other issue. An injection locking process was used to synchronize the oscillator, and reducing jitter made sure that there was low power consumption, which means there was lower leakage. In December of 2019, TSMC made an announcement that this actually increased the yield by 80% and 90% for their 5nm test chips with a die size of 17.92 millimeter square. This 5nm process has 300 million transistors per mm square of transistor density, which is a huge number. Now let us talk about what can be the future of this. As you can see in the figure, the journey has been from planar to FinFETs, and now it will reach to GAA probably. These are the types of MOSFETs that were used for a technology. Until 5nm, a FinFET could be used, but now scientists think that to advance to 3nm process, we need a more better technology for a MOSFET. So they are planning for GAA, which is gate all around MOSFET. There's not much difference between a FinFET and a MOSFET, except for the fact that in FinFET only 3 sides are covered with gate, whereas in a GAFET all the 4 sides will be covered by gate, so there will be least leakage possible. One of the key challenges of engineering future nanoscale transistors is to design this GAFET to shrink the device size and control the current flow in thin channel becomes difficult. That is why a thinner FinFET than that used for a 5nm process is not possible. So as I already said, that the difference between a FinFET and a GAFET is that a FinFET has gates on 3 sides of the channel, whereas a GAFET has gates on all the 4 sides. This gives better gate control. Another option for GAFET is a MBCFET, which is multi-bridge channel field effect transistor. The difference between GAFET and MBCFET is also not much. GAFET operates on nanowires, whereas MBCFET are using nano sheets. So the gate keeps covering the channel on all the 4 sides, but in GAFET the channel is a wire, whereas in MBCFET the channel is a sheet, which gives more area, which implies more control. Samsung declared production using this technology. This is comfortable with the existing FinFET process, so it can be used as of the current times. The commercialized 3nm node is expected to hit the market by 2022. Production for special customers has already started. The research is carried out in figuring which transistors would be best to implement the 3nm node at this point. But most forecasters, including Gordon Moore, believe that the Moore's law will end by around 2025. There wouldn't be any further development. These are the references I have used to prepare the presentation on 5nm Next-gen Semiconductors. I hope you like the presentation. In the end, all I want to say is that Moore's law, Dennard scaling, and Kumli's law combined are running the semiconductor industry. The 3nm process is to be out soon, and the commercial use will be by 2022, which is very important. It will advance the technology, increase the performance, and decrease the time used to actually execute an instruction. This is how the future looks. Thank you very much.